Good day, this is Jim Pytel from Columbia Gorge Community College, Renewable Energy Technology Program. This is RT 120 Hydraulics. We're going to have a quick discussion today about a very common device, and that device is the check valve. The check valve's whole purpose in life is to allow fluid flow in one direction, but stop it in the other direction. Okay, what we see right here is a pictorial diagram of a inline check valve. Not very telling, because what it looks like a brass valve with an inlet hose and an outlet hose or pipe hooked to it. But what we see is this arrow engraved on the side of it. And sometimes it will also have the schematic engraved on the side of it. We're going to come back to what the schematic is and what it means in a second. But what that arrow engraved on the side of that particular valve is implying that is the direction of free flow, i.e. fluid can flow through there unimpeded. Whereas if fluid tried to flow in the opposite direction, it would be stopped. Okay, so as I said, the pictorial diagram not so telling. So typically I would jump to the cutaway, but I'm actually going to jump to the schematic here with a little discussion about the schematic. This is the schematic for a check valve, typically used. Sometimes you'll see a little spring right here. And that's quite literally what it is, especially for a ball and spring check valve. It is quite literally a ball being held to a seat by a spring. And if we think about it, if this is the direction of free flow, if fluid was coming in, it would push the ball off its seat as long as it could overcome the spring pressure and continue to flow through. But if fluid tried to go the opposite direction, it would force the ball on its seat and close that passage, and fluid could not go through. So the schematic symbol for a check valve always tells you what the function of it is. And this is the schematic symbol you will often see, with or without the spring. Okay? So let's look at a cutaway view. Here is a cutaway view of a direct acting check valve. Direct acting meaning the high pressure fluid is acting on the ball and spring. In this particular case, it's not a ball. It's known as a poppet, which is, for all intents and purposes, a ball. Behaves the exact same way. What you see here are the cutout, the half, basically that you've sawed the valve in half, and you're seeing the spring there. And the spring's whole purpose in life is to make sure that the ball, or in this case a poppet, is seated on that particular seat right here. And so we've got port 2. It looks like we've got red, which we're going to go ahead and say that that is high pressure fluid trying to go in one direction, and it's forcing the poppet against the seat. So what's happening there is there's no flow because there is pressure trying to go that direction. It's holding the poppet, or in this case the ball in the schematic version, to the seat, and flow will not pass through that seat. Whereas if we go to this other diagram here, we have high pressurized flow coming in inlet 1, and it's acting on the face of the poppet, moving it off its seat and allowing fluid to flow in this direction. Unrestricted, free flow. So where are you going to see check valve? You're going to see them all over. Namely, one of the first applications you're going to see is hoses, especially for mobile equipment. You've got a hose coming out, and this is to a piece of a mobile equipment right there, and this is some hydraulic system. And notice how if flow tries to go this direction, it's forcing the ball against its seat, i.e. it's not going to open. But what if you had a matching pair of these quick disconnect fittings with check. And that's exactly what it is. Here is a quick disconnect fitting. Disconnected. Here is the same fittings. Here are the same fittings. Connected. And when the ball is off the seat, it's implying that when you hook them up, the very act of hooking them up physically unseats the ball from that. And fluid can flow, in this case, in either directions. I know I'm countering myself for what I said earlier, where a check valve allows flow in only one direction. What I'm saying is this is a different specialized application for our typical one-way check valve. The very act of connecting them, in this case, unseats the ball. Okay, so let's go into another application for a check valve that you're going to see quite a lot. And that's what's known as a bypass. If you could imagine a filter, and I'm using the schematic symbol for a filter, which is a perforated diamond-shaped item. And if you know anything about filters, that's exactly what they are. That's a series of perforations that are filtering out contaminants. Imagine if this thing becomes, and let's say it flows going this direction, clogged with a bunch of contaminants in here. What would happen? Basically, eventually this thing would close down and no fluid flow could develop and pressure in your system could expect to rise. So oftentimes there's a check valve bypass. And you're going to see this in a number of devices. Checked bypass. What's happening here, as long as fluid is flowing in this direction and the filter remains relatively clean, fluid is going to continue to go through the filter. But if contaminants start building up in here, what's going to happen is the pressure differential across this filter is going to increase, and basically there's going to be a pressure on this upstream side. It's going to start increasing. And what's happening here is this spring that's seating the ball to its seat, there is a force that it's holding to, and if that pressure differential, if that pressure on this upstream side exceeds that force being applied on the surface area of the check, basically what's going to happen is that ball will unseat. So implying that we've got a dirty/clogged filter. And if it's clogged enough, it will eventually unseat that and allow fluid to flow through. What's happening here is an unideal event, because what you're happening here is dirty fluid going through here. But what this is often used for is an indicator. It allows the system to operate temporarily with dirty fluid, but sometimes what's hooked to that check valve bypass is some scale. Green, yellow, red. Green means the check valve is closed and fluid is being filtered by a good filter. Yellow implies that the check valve is fluttering on its seat. Basically, there's enough pressure to push that thing off its seat, and you might have a potentially clogged filter. Red means it's fully bypassed. It means whatever system you're using now, it's going to allow you to temporarily operate it for emergency situations, but you should, for the life of that system's components, go ahead and cease operation and change that filter. Okay? This is not the only time checked bypass is used. One of the things that we're going to be discussing in greater detail is what's known as a flow control valve. And a flow control valve basically controls the amount of fluid going through an orifice. An orifice is an opening, and basically what this is saying, this arrow is adjustable. And let's say I'm adjusting this down to 6 gallons per minute flow in this direction only, okay? But let's say I want full fluid flow in the other direction. Let's say my system was limited to 10 gallons per minute, and I wanted to make sure that whatever actuator over here only got 6 gallons per minute. But when I reverse flow, I want to go at full 10 gallons per minute. How would I do that with this flow control valve in the way? Well, there's a problem. So how you do that is you actually insert a check valve bypass in parallel with the flow control valve. Now I'm going to leave it to you guys to think about what is the proper orientation for a check valve to go in here to allow unrestricted flow in this direction and restricted flow in this direction, implying that any fluid going down this channel is blocked. And the answer is this is the correct orientation. Because as we just discussed, free flow fluid unseats the ball from its seat and it will allow full amount of fluid to go. Whereas if fluid tries to go down this path right here, it's forcing the ball in its seat. It has to stop, thereby forcing the fluid to go through that restricted orifice, which restricts it to, in this particular case, 6 gallons per minute. Don't worry so much about flow control valves right now. We're going to go back into those in greater detail. But that's a bonus schematic that you get for today. That's a flow control valve variable. Okay? So this is really the level of detail we need to go into right now. But one of the major things you need to understand about check valves, what's its whole purpose in life, is to allow free flow in one direction and stop flow in the other direction. And getting the orientation of these valves correct in your circuits is going to determine whether your circuit operates as expected. So again, just for a reminder, free flow in this direction because it pushes the ball off its seat. No flow in this direction because it forces the ball to its seat. Okay, and again, if you get an inline valve, if you buy one, chances are it's going to have engraved on its side an arrow indicating the direction of free flow, and chances are they're going to have the schematic also drawn on the side of it and their part number. Okay, we are going to revisit the check valve a little bit later. This again serves as only introduction.